Suppose you're looking at a tree through some binoculars. The question I have is, what's actually going on with the light that comes from the tree into your eye? Okay, we're going to try and describe that process in more care than we would just going on a walk looking at a tree. I don't even think about it. But if we consider the physics of that light propagation, we can come up with some really cool applications, some of which we use all the time. I'm wearing glasses right now to correct for nearsightedness, allowing me to be able to see much better. And so these applications are extremely important and broadly applicable. So to start off, let's suppose I'm staring at a tree. So here is my best effort at a tree. I know what you're thinking, that's a horrible tree. Okay, that's alright. I'm going to say it's on the ground. Right there. And I'm standing somewhere far away looking at it through binoculars. Okay. First of all, the question is, how does light come off the tree? Well, the tree doesn't glow. Well, the way we see a tree is because sunlight comes down in all directions, hits the tree, and some of the light's absorbed and some of the light is reflected or scattered off of it. Okay, so some of that light gets scattered off, and it goes in all directions. No matter where I am standing around the tree, I can still see the tree if I look at it. Okay, so light's coming off this in all directions. Even from the same point, okay, that point right here, light can be coming off of it, scattering, the sunlight scattering off of it in all directions, because I can see that tip of the tree from all positions everywhere. Okay, so that's the first thing to think about, is that the light is coming in all directions from every part of the object. Okay, now let's go towards these binoculars. Let's just assume a simple lens. Okay, I'm going to draw a convex lens. We're going to go over the details of a convex lens later. Okay, but I'm going to draw this really big lens, which is an exaggeration so I can show the details of this principle. All right, and I'm going to, this tree's sitting there on the ground, but I'm super far away, and so that tree is actually crazy small, and I have it centered in my lens. To help with that, I'm going to choose a line, and I'll just go ahead and choose it to be this line right here that I've drawn, that goes through the center of my lens. Okay. Now, technically, my lens might be over here, and I'm looking at that. That really doesn't matter for this description. Okay, my goal is what's happening to these scattered light rays as they pass through that lens. Well, one thing about these lenses, which we'll do the math a little bit later using Snell's law, but they end up having what's called a focal length and a focal point on either side of this lens that are associated with the curvatures of these two sides of the lens. Again, that math is a subject for a later video, but what's important here is that there is a position, let's say right here, that's some distance away, okay, that far away, that we call the focal point or focal distance for this lens, and there's another one on this side that's the same distance away. Okay, these focal points. I tried to draw that same distance away. It wasn't very good, but okay. So these are called the focal points. This is the focal point associated with this second surface over here, and this is the focal point associated with this surface. Okay. Now, what's happening to light rays? Well, light's going in all sorts of directions. I've got light going that way. I've got light going that way. I've got light going that way, and every other direction. Okay. But it just so happens that I can describe very quickly what's going to happen to at least three rays. Okay. One of them we call the parallel ray. It's the ray that enters the lens parallel to this axis here, this axis that goes straight through the lens, the center of the lens. We call that the parallel ray. And the thing we know about that ray is when it comes to this midpoint of the lens, okay, it bends such that it goes through the opposite focal point. Okay. Then we have a focal ray that goes through the near focal point and then comes out parallel. So it's kind of the reverse of the parallel ray. Right? And if light was traveling from over here that way, they'd follow the same paths. Okay, we're going to focus the light going this way. Okay, those two rays are kind of our guiding rays. They tell us what's going on, and wherever they cross, that is where the image of this piece of the tree is going to be. And so I'm going to have this tree leaf there. It's going to be right at that point. That's where the image would form. What's really cool is, we're not terribly used to seeing images outside of the idea of I'm just looking at something, the light's coming and forming this image on the back of my eyeball. But literally, if I stuck a piece of paper right here, and this light was bright enough, I would see a picture of the tree, a nice crisp image of the tree on this piece of paper. So you don't need to have an eyeball to be able to see that. The screen itself could form that image. Alright? And so wherever these rays cross, we know that's the case. Now what if I messed up on one of these rays, if I got it off just slightly? Well, there's another ray that can help you check and make sure you did it right. That's called the central ray. So there's another ray that's coming off here, and it goes through the center of the lens and undeterred. Whatever it does on one side, it does the same thing on the other side. So it goes straight on through. And if it crosses through that point too, you know you've done it correct. So we have these three rays that we can use to figure out where the image is going to be on the other side. Okay? Now I could have done it for this point as well, and if I followed those principles, I would have gotten something about right here, and here, from this piece I would have gotten something about right here, and from the base of the tree I would have gotten something about right here. And what basically happens is you get, for this lens, we get kind of an inverted, and I can't draw upside down, so forgive me, but we get kind of this inverted tree. Okay? That's the basic ideas. We have these three rays that we use to be able to determine the focal point. Now before leaving this video to go do some examples of specific lenses, I want to talk about, are these the only three rays? And the answer is no. What about that one? Well, that one's going to go off, hit this lens way up here. Okay, I haven't drawn the lens properly, or big enough to capture that ray, but if this lens went a bit, if this light ray did end up going through this lens plane, it would bend. But I don't have any good rules for that one, except once I found where the focal point is, I know that that ray is going to come, or sorry, once I found where the image point is, I know that that ray is going to come down and go through that one. Similarly, I could pick one that goes through some random spot up there. I know it's going to come down through there. I could go down here in between these two rays, and I know it's going to go right there. And anywhere else I could pick, I know that they're all going to converge right there. Okay? So though we have these three rays, we need to remember that they're not all the rays. They're only a very small fraction of all the rays that are going through this lens. This lens captures all the light that goes through it and will focus it to that point. And so we have the three just as guiding rays to figure out where it's going to be. But we have all these rays that actually form the image there.